Hello, my name is Franco Zunino, and I'm pleased to offer this Rock and Talk webinar for Rilem on the technological breakthrough of limestone calcined clay cement. How much further can we go in the sustainable concrete endeavor? Concrete is everywhere around us. We use it to build our houses and infrastructure, in dams to obtain energy, but it's also part of our sustainable development strategies. We will continue to require massive amounts of concrete to materialize these new technologies. Concrete is therefore the second most used resource after water by humanity. The Portland cement that we need to make this concrete is then accountable for about 7% of the industrial energy use and about 8% of the anthropogenic CO2 emissions. The best estimates we have only forecast that this demand for cement will continue to increase in the next 2 decades, particularly in regions that are facing development such as India, Africa, and Latin America. LC3 is a blended cement that combines clinker, calcined clay, limestone, and gypsum. It allows us to reduce the clinker factor of this blended cement to 50%, saving 30 to 40% CO2 compared to PC, and offering equivalent performance to PC in terms of strength and enhanced durability in some exposure conditions. Why it is important to consider calcined clay and limestone as supplementary cementitious material? The main reason is that these materials are the only that are available in the quantities we need for a widespread reduction of the clinker factor. Particularly here, I want to analyze the case of slag and fly ash, which are two materials that are widely used to blend cements. In the case of slag, the stock that we have worldwide is about 8% of the cement production, and it's actually decreasing as we recycle more steel rather than producing from iron ore. And in the case of fly ash, as we shut down our coal power plants, it's expected that this material will disappear by 2050. Concrete is a sustainable material. When we compare concrete with other construction materials, we can actually see that the embodied energy and the embodied CO2 is much lower. So then where is this high environmental footprint coming from? It's because we use a lot of it, and we will continue to need a lot of concrete to continue developing our society. Despite the relative low environmental impact of concrete compared to other materials, we still have significant space for improving, and this is what I want to show in this presentation. What are the strategies that we can focus our scientific and practical development in order to achieve a lower CO2 material for our future development? The CO2 of concrete is coming mainly from the cement that is used as a binder to connect the aggregates in the material. Approximately 850 kilograms of CO2 are produced per ton of clinker that are emitted. In this sense, the best strategy, and this is the focus of most of the research on sustainable Portland cement in the last decades, is to reduce the amount of clinker by incorporating what we call SCMs, or supplementary cementitious material. In short, we need to use blended cements. But, and I want to be very clear, the construction material is concrete, not cement-based. And it's very important here that at the end of the day, we need to think in terms of total binder content, which is cement plus SCMs per cubic meter of concrete. And this is a multi-factor problem because this quantity depends on a lot of other requirements such as slump, maximum aggregate size, the aggregate grading that I use, my choice of water to cementitious material ratio, depending on the strength and durability requirements that I may have, and the use or not of chemical admixtures. So at the end of the day, this is a multi-factor problem. And in this regard, the performance of our blended cements is key, as I will illustrate in the next slides of the presentation. LC3 is a good cement for the future. It offers equivalent performance to Portland cement. And this is very important because in this case, we do not need to decrease the water to cementitious materials ratio compared to PC in order to obtain a certain strength in our concrete. And this allows me to keep the binder content per cubic meter of concrete low, or as low as I would use in a Portland cement scenario. This allows me to save 40% of CO2 compared to PC, and I have enhanced durability properties against chloride, sulfate attack, and ASR. What explains the good performance of LC3 cements, what makes LC3 so special that I can reduce the clinker content 50% and still retain the same properties as PC in terms of strength and even improve some of these properties in terms of durability. During my doctoral process, I explored different aspects of the LC3 technology, from the clay quarry to production of the blend and characterization of its properties at early and long-term ages. In particular, I conducted studies on the effect of calcite and pyrite impurities on the reactivity of the calcined clay, the use of particle classification techniques during grinding to increase the kaolinite content of low-grade clays, the application of grinding aids, particularly alkanolamines on LC3, in order to improve the grinding process and also develop strength over time by interaction with the aluminate phases. The sulfate balance of blended cements, and particularly LC3, is something that I study in detail and that I will talk in depth during this presentation. What makes LC3 so special, which is the precipitation of carboaluminates in LC3 by the interaction between limestone and calcined clay. And finally, the long-term behavior of LC3 and how these reactions continue in the long term to provide consistent strength and durability of the material. We need to understand that the hydration process of a cement is a compilation of chemical reactions taking place one after the other or simultaneously, and these hydration reactions translate into microstructural densification, what we call space filling. And it's really this space filling, this microstructural densification, what provides me with strength and durability. In the case of LC3, we have a certain classical calorimetric profile that we see here on the left, where we have a first hydration peak associated with halide hydration, a second hydration peak associated with Ettringite precipitation, and a third hydration peak, which is linked to the precipitation of carboaluminates. And it's really important to realize at this point that the precipitation of CSH, Ettringite, and carboaluminate contribute to strength during the first days of hydration. In this presentation, I will focus my attention on the second hydration peak linked to Ettringite precipitation and the third hydration peak, which is associated with the precipitation of carboaluminates. I want to move now to talk a little bit more on the work that we have done at the EPFL on sulfate balance and carboaluminate precipitation of LC3 cement, and how important is to understand the underlying mechanisms to optimize the performance of these blended cements. Why we need to study sulfate demand in LC3? Well, this is important because in some cases we can end up in a situation like the lightest gray curve here, which is what we call an undersulfated system. This is when the aluminate peak occurs first, followed by the second halide peak. In this case, the halide peak, which follows, appears depressed, and we have a lower degree of hydration of halide at 24 hours, compromising the early age strength of our blended cement. Fortunately, there is an easy solution for this, and we have known this for more than 100 years. We can add gypsum or another sulfate source to the system in order to retard this aluminate reaction. And in this case, the silicate or halide peak takes place first, and the aluminate peak follows. In this case, the silicate peak recovers its normal development, and the aluminate peak takes place after depletion of solid gypsum in the system in what we call a properly sulfated system. But why LC3 has a higher sulfate demand compared to PC? Why we need to add more gypsum to LC3 compared to a normal PC, even accounting for the dilution effect of the clinker factor reduction? And for a long time, we believed that it was the alumina introduced by the addition of metakaolin, an amorphous aluminosilicate, into the system. The problem is that this correlation is not systematic, as we see in the plot here on the left. We have a system with 50% metakaolin addition, which exhibits a higher sulfate demand than a system with 95% metakaolin addition. We can see that both systems have the same gypsum addition, and in this case, the peak occurs earlier in the system with lower metakaolin. The difference between the two clays is that the lowest grade clay, lowest grade meaning lower metakaolin content, has a higher specific surface area compared to the higher metakaolin content system. And we can see that by the increased enhancement of the Li peak in the case of the 50% metakaolin system. So it appears that the acceleration of the aluminate reaction is more related to the filler effect contribution of the calcined clay rather than the alumina contribution of the material. And in order to confirm that, we replace calcined clay by a material that doesn't contain any additional alumina, in this case, a very fine limestone powder, but it offers the same surface area contribution as calcined clay. And we observe the same type of enhancement of the alumina reaction as we see on LC3 on a system, in this case, that it actually has less alumina than the control PC that we have down here. So in this case, we were able to confirm that is the contribution of the surface of the SCMs through what we call filler effect, what explains the higher sulfate demand or the increased sulfate demand of LC3 and in general of any blended cement. But the question is then how the filler effect is linked to gypsum depletion, because filler effect is something that we normally relate to halide reaction enhancement, and this is a separate chemical reaction involving alumina. And the answer to that is CSH. CSH, as we know, is the main reaction product of the hydration of cement, and it's well known that it can absorb and incorporate different ions during the hydration process, particularly sulfate, that as we are concerned here, but it can also incorporate things such as alumina, alkalis, and chloride. We can see here from previous work in our lab that the amount of sulfate in the CSH is very high before the aluminate peak, and then it decreases as the aluminate reaction restarts after depletion of solid gypsum in the system. So basically what this shows us is that sulfate is absorbed on CSH and then is dissolved at gypsum depletion. This allows us to formulate our mechanism of sulfate balance of LC3 and in general of any cementitious material. We can divide this in two stages. During the first stage, sulfate gets absorbed in CSH surface. And it's very important here to realize that if the rate of CSH precipitation is increased, sulfate absorption will also increase. In this regard, finer material as finer clinker, for example, hydrate quicker, consuming more sulfate per unit time. So this cement will have higher sulfate demand. And the addition of more nucleation surface, what we call fillers, which is basically what supplementary cementitious materials are doing, will affect the CSH precipitation rate and therefore the sulfate balance. But this contribution is in general independent on the chemical composition as soon as the chemical composition is not affecting significantly the filler capacity of the material. In particularly, this is not directly related to the alumina content of my material. In the second stage, and the hydration keeps going, gypsum is depleted from the system, triggering the desorption of sulfate from CSH, which then reacts with the aluminates to form ettringite during the second ettringite formation, which we associate with our aluminate peak. Let's move now to precipitation of carboaluminates in LC3 and why this formation, this enhanced formation of carboaluminate is so special and makes LC3 such a special blended cement for our sustainable concrete endeavor. So summarizing what we know now, we have three main peaks that we can clearly identify during LC3 early hydration. A first halide peak associated with dissolution of C3S, leading to precipitation of CSH. A second aluminate peak associated with the fast dissolution of C3A, leading to the second precipitation of ettringite, as we discussed in the previous slide. And we have this third peak of hydration. And we wanted to understand which reaction was associated with this third peak of hydration, which appears enhanced in LC3 compared to what we see in Portland cement. And for this, we analyzed the different reactions happening in LC3 that involve metakaolin on them. So the first one that we see here is the classical pozzolanic reaction, if you want, where metakaolin reacts with portlandite and water to form CaSH. In addition, it's well known that limestone or calcium carbonate can react with alumina from clinker, with the alumina from C3A mainly, to form what we call carboaluminates, monocarboaluminate and hemicarboaluminate. And in LC3, we have a third reaction, which we call the synergetic reaction, where the aluminates from calcined clay replace the alumina from clinker, because we have another source of amorphous alumina here, very reactive, and can react with the calcium carbonate and portlandite in order to form more carboaluminates. That's what I would observe in the case of a cement not incorporating calcined clay. By systematic exploration of these different reactions and by doing selective experiments to try to decouple these different effects, we were able to associate this third peak of hydration with this reaction here, what we call the synergetic reaction between metakaolin and calcined clay. Carboaluminates precipitate in the microstructure of LC3 in grains, filling large pores that are left behind by clinker hydration. And this is really important because AFM phases, and in particular in this case, carboaluminates, contribute significantly to porosity reduction at early ages. We can see here in this colorized micrograph using elemental mapping to identify by clustering the different phases. Everything in red correspond to carboaluminates, and we can see that all of these pores were filled with carboaluminates, and this is significantly contributing to the development of mechanical properties at early age. We can see higher magnification micrographs on the right, where we can see that carboaluminates integrate really well with the matrix of CSH surrounding it, and also with other aluminate hydrates like ettringite, as we see here. In the micrograph in the bottom, we can see an unreacted metakaolin particle and AFM precipitating and filling spaces in between. We were able to confirm the contribution of carboaluminates to mechanical properties by using in situ ultrasound pulse velocity measurements. But to do this, we use two systems that have a consistently different third peak of hydration, which we know now is associated with the formation of carboaluminates. And we perform this measurement that basically provides an estimation of the development of mechanical properties over time. And we can see the same kind of detachment between these two systems as we see in the calorimetry results. So this basically tells us that the formation of these carboaluminates is leading to a quantifiable and a measurable reduction in porosity and increase in mechanical properties. And this is very interesting because it's really where this separation occurs between 2 and 3 days of hydration, where we see the highest correlation between metakaolin content and compressive strength of our LC3. Then we can also conclude that if we can increase the amount of hemi and monocarboaluminates, we can likely increase the strength properties of our LC3 as well. For example, by using alkanolamines as grindiness. And this is a side study that we did during my doctoral process. And we could confirm that by using things such as TEA, triethanolamine, in the calcined clay, we can not only improve the grindability properties of the material, but we can also enhance the strength development of the material by promoting the formation of hemi and monocarboaluminate. We do observe a slowdown in the formation of carboaluminates over time. And it's very curious that this slowdown occurs first in systems with higher metakaolin content and occurs later in systems with lower metakaolin content, as we see here in the plot. In the beginning, the higher the amount of metakaolin in my LC3, the higher the amount of hemi and monocarboaluminate that I form. But as early as 7 days, we have a reversal of this trend, and we observe lower amounts of carboaluminates in the higher grade systems, and the higher amounts are actually observed in the medium grade ones. The reason for this is that the precipitation of hemi and monocarboaluminate leads to a porosity reduction and a decrease in the critical entry site in the porosity of our material, as we see here in the plot. And this refinement occurs earlier in systems with higher metakaolin content. We can see here that 95% becomes refined as early as 2 or 3 days, while the system with 20% metakaolin takes about 7 days to reach the same degree of refinement. The reaction then slows down earlier in systems where only small pores remain saturated, in this case in systems with higher metakaolin content, And this is why we observe lower amounts of carboaluminates at later ages. However, I want to emphasize that the reaction is slowing down, but it's not stopping. And slow precipitation still occurs at early ages, as we can see here in the plot, where we compare the amounts of AFM, carboaluminate, monocarboaluminate, and stratlingite between 90 days and 3 years. And we can see that in all cases, in all of the systems studied, the amount of AFM increases over time. So it continues to precipitate, but at a much slower rate in the long term. Particularly, in addition to Emi and monocarboaluminate, we also observe stratlingite, which is the third type of AFM phases. And in this case, we can also observe that the experimental phase assemblage that we can observe in the long term start to approach more to what we can compute by thermodynamic modeling. In two ways, we observe stratlingite in our high-grade systems with metakaolin contents above 47%, and also because the proportion of Emi and monocarboaluminate increases towards monocarboaluminate, which is also something that is predicted by thermodynamic modeling. In terms of precipitation, by coupling MIP measurements with internal relative humidity measurements, we were able to propose a dual mechanism for hydrate precipitation in the long term. By using the internal relative humidity measurement, we are able to compute the largest pore size that remains saturated with pore solution, and all of the rest of the porosity basically remains partially saturated or only covered with a film that lines the internal surface of the pores. And the largest porosity reduction is indeed observed in the saturated portion compared to the slight reduction that we observe in the fraction that remains partially saturated. But important to mention that we still see some reduction in this area. In this case, we propose that there is a dual mechanism. So in small pores that remain saturated, so in this area, we have conventional precipitation of hydrates because we have pore solution saturating the pores. And in pores that are larger than that, so they are only partially saturated or covered by a film lining the internal surface of the pore, we have slow precipitation in this solution film that covers the surface of the pore. Finally, to close my presentation, I would like to offer an outlook and some perspective of the LC3 technology and some thoughts of how and what can we do to increase the CO2 saving potential of this technology and in general of the concrete industry. Personally, I consider that the golden rule is that we need to develop and use blended cements with the least amount of embodied CO2, which it's in most cases proportional with the lowest amount of clinker, but very importantly, that have sufficient performance to enable their use without a significant increase of binder content per cubic meter. And this is what I call the twofold strategy. We need to consider the two scales simultaneously because otherwise we will not achieve the optimum CO2 reduction per cubic meter of concrete. We need to consider simultaneously the CO2 of cement, which is proportional to, or the same as saying, we need to reduce the clinker and retain, as I said, or improve the performances we can. And we need to, at the end of the day, reduce the CO2 of concrete. So we need to reduce the paste content while remaining still workable, strong, and durable. And this is very related to the development of more advanced admixtures that enable us to do this in a more efficient way in the future. And this is where the LC3 technology becomes a breakthrough because it's, to my knowledge, one of the few solutions, if not the only one, that enable a substantial clinker reduction while retaining the same mechanical performance as PC. And this is very important because it's able to link very efficiently the two components of the twofold strategy. Also, a sustainable concrete conceived in this way is most of the time cost effective because we are reducing in these two elements of the twofold strategy the amount of cement, which is the most expensive component of concrete. To illustrate the CO2 saving potential of the clinker factor reduction and the binder content reduction, I would like to illustrate that with this kind of illustration animated illustration that I prepared here. So I took a typical cement from the European market, a Portland limestone cement with 85% clinker, 10% limestone, 5% gypsum, and I assigned to that 100 units of CO2 per cubic meter of concrete at a binder content of 375 kilograms per cubic meter, which is also a typical number or combination used in the Swiss market. If we analyze the clinker reduction element and we take something like LC3, which enable us to go 50% clinker down, we move to here. We know that LC3 enable us to save 40% of CO2 compared to BC. And even by not doing anything at the concrete design scale, we can save 40% of CO2. And this is why this is so important, because since LC3 retains the performance of PC, we can do this without having to modify our water to cement ratio. If we then start working on our concrete mixture design and we reduce the binder content, we can see that we can also reduce significantly the CO2 units per cubic meter of concrete. Of course, doing the two things at the same time leads to the best reduction in CO2 per cubic meter of concrete. But I want to emphasize here that the two strategies, reducing the clinker factor and reducing the binder content per cubic meter of concrete, have similar potential to reduce the CO2 of our construction material at the end. So we really need to tackle both in order to have the best results. In this regard, at the concrete scale, I would like to address three elements that I consider very important in order to achieve low CO2 concrete mixtures. And these cover aggregate selection and aggregate grading, the use of chemical admixtures, and of course, what we have been discussing during the whole webinar, the use of SCMs. In terms of aggregates, we need to realize that aggregates constitute about 70% by volume of our concrete. So our concrete, volumetrically speaking, is mostly aggregates, and the cement paste basically fills the spaces between these aggregates. We need the cement paste to coat the surface of the aggregates because it acts as a lubricant between them. And this is what enables flow at the fresh state of concrete. So we need a certain amount of paste, but we want this amount to be as low as possible. And there is basically two things at the aggregate scale that we can do to achieve this. We can increase the maximum aggregate size when possible, and we need to tend to use largest aggregate sizes when we can, and to design our structure to enable this if possible. And also we need to use good grading of aggregates. In an ideal situation, what we would like to have is a concrete with more than 70% of aggregates and less than 30% of volume of cement paste. In terms of chemical admixtures can enable us to achieve certain properties such as length, early age strength, shrinkage, beyond the envelope of not admixed concrete, and reduce the amount of embodied CO2. And I would like to illustrate this with an example with a super plasticizer. So if we take a typical concrete with a water demand for slump of 200 kilograms per cubic meter, and we decide to formulate this concrete with no super plasticizer or with 1% super plasticizer addition that enables me to reduce the water content 25%, we can then compute the amounts of cement that we are going to need, the amount of super plasticizer that we want to need in this case. And if we then take reference numbers for CO2 calculations, and we compute the carbon footprint of these two concretes, we can see that the use of the super plasticizers enables me to cut 23% of the CO2 per cubic meter of concrete just by applying this strategy alone. Other types of admixtures, such as accelerators, aiding trainers, etc., can enable us also to achieve other properties of interest in our concrete. So it's very important to consider the use of admixture as a way to reduce the carbon in our concrete designs. Reducing the clinker factor with poorly reactive SCMs can lead to a situation where the binder content per cubic meter of concrete has to increase to achieve a certain strength. This is basically reducing the water to cement ratio, and since we have a water demand for slump, we will have to increase the amount of cementitious materials, and we can end up actually with a concrete that has a higher embodied CO2 content compared to our base scenario. So this is why, again, LC3 is so special, because it offers equivalent performance to PC at 50% clinker reaction. But PC level strength is not always required. And this is an opportunity to reduce the clinker factor even further down. And we did trials with what we call LC335 with 35% clinker, where we don't achieve the same strength level of PC as we do with LC350, but we still achieve something that is above 40 megapascals at 28 days. A large part of the strength reduction is offset by the precipitation of carboaluminates in the system. If we then compare LC3 to pozzolanic cements of the Chilean market, both of the high strength and general use grades with 80 and 65% clinker, we can see that we can achieve the strength requirements of this standard with 35% clinker and 25% clinker if we use something like LC3. So we meet the high strength requirement of the Chilean standard with LC350 or LC335, and the general use one with actually LC325. There is a small typo there. This leads us to clinker savings compared to pozzolanic cements of 45% in the high strength grade and 40% in the general use one. So a huge opportunity to develop lower CO2 cement, even in markets where PC level strength is not required or is not used to be implemented in the standards. So as final remarks, I would like to highlight that LC3 is a good cement for the future. First, because the raw materials are widely available, and also, and very importantly, because it offers comparable performance to PC. Understanding the fundamental mechanisms of sulfate balance and carboaluminate precipitation are key elements to optimize and formulate better LC3 cements. This twofold strategy that I mentioned at the last part of my presentation enables the consideration of other factors in the concrete mixture design towards low CO2 formulations. The strategy highlights the importance of performance in blended cements. There is additional opportunities at the concrete design scale. I mentioned three of them: use of admixtures, aggregate design, and the use of high performance SCMs. In addition, we can use formulations of LC3 with lower clinker contents below 50% in lower strength applications. With this, I would like to thank you for your attention. I would like to acknowledge the State Secretary for Education, Research and Innovation for funding my PhD studies at EPFL, and the Swiss Agency for Development and Cooperation, SDC, for supporting the LC3 project at EPFL as well.